Hi everybody, and re-lab questions. So, welcome to class, blah blah. Today you've got the lab exam. It's over the blood lab, which, come see me, I can get back to you. Over the blood lab, the muscles lab where you threw ATP on it and watched it shrink, and the nervous system lab. Over those three, and over your self-design experiment. I mean, I can pull, it's timed an hour. It's got 2 questions from each lab, except neuroscience has 3 questions because they're really small. I legitimately think people are going to probably get 90 to 100%, assuming they do it, because, like, well, let's just open it up right now. Let's briefly see this. Wrong course.
So there's only 7 questions?
Yep. Should be fine. You like, no, this was supposed to be a happy thing.
Yeah,
This,
I know.
oh, okay. I don't know if it's like, hasn't they taken it yet? Exam 2. I'm gonna show it to you for like 1 minute, which I don't think is cheating because I will tell everybody what's on it. Hi, online peoples. Let's see. Know about blood types, who's what, anatomy of the heart, what happens when, what does calcium do in muscles, what does ATP do in muscles, what's an action potential, how do ions work in action potentials, and how come action potentials don't go backwards. And remember, you're doing your self-science experiment. It's open book, it's timed an hour, you all will be great. Like, assuming you do it and like, yeah, you'll be fine. Questions about what that covers? It does feel weird because normally, in a normal year, I'd have little jars of fake blood and be like, what type is this? Or,
you'd have to actually do the test.
yeah, or for like the heart anatomy, I actually was starting to write this like long convoluted thing, like what are all the parts here? And then I realized all I was asking was, can you find an image in your book and match the labels is really what I was asking. I'm like, that's just dumb. So now it's like, what does this part of the heart do? What does that part of the heart do? So it's a written question rather than, because normally lab is just the memorization thing, but now it feels really weird, right? It's like, how do you, all it's saying is, can you Google search for images and be like, yeah. This, I do feel sort of bad because I feel like you all are getting a less good lab experiment. I don't know. So many things I don't know about. Yeah, it's gonna be like a weird year, and like you'll be fine. Like you'll know the information will be great, but it's a weird year. And every time, sorry, this is like probably too personal. Every time I get to the point where I'm like, I'm just done with it. I'm gonna go cough on strangers in public. One of the kids in uh, the Gen Bio class comes to me in tears about their grandparents dying, and they're gonna be gone for a couple days. I'm like, okay, fine. I'll stop. Yeah. Okay, so we're on to blood today, and blood is really interesting. Are we questions about what's happening in life? Okay. Blood's interesting, and a lot of people are actually weird's a bit strong. Kind of weird about blood. So like, they can see, um, like they can see bones and be just fine. People can see muscles and be just fine. But more people than you'd expect get kind of odd about blood. And I actually have a YouTube video to show you. Alright, this isn't. Yeah, this one. Online folks, if you go on YouTube, it's Why do people faint at the sight of blood? By brain stuff. Sorry I put the link in.
Hey, and welcome to Brain Stuff. I'm Josh Clark, and this is the Brain Stuff where I explain to you why some people faint at the sight of their own blood. Fainting at the sight of blood, which is a condition called either neurocardiovascular syncope or vasovagal syncope, is actually related in some cases to what's classified as a blood injury phobia. Now, something like 3 to 4% of people have a blood injury phobia. But what's really interesting is that 15% of people faint at the sight of blood, which means there's a lot of people out there who really have no issue with cutting themselves, but still faint dead away anyway when they see themselves bleeding. That's kind of weird. Now, when you faint from anxiety, which is what researchers think is going on when you faint from the sight of your own blood, your blood pressure suddenly spikes, but then just as quickly it decreases. And that decrease in blood pressure drains blood away from your brain, causing you to lose consciousness. Now, when you're anxious or when you feel like you're in danger, it's normal for your blood pressure to rise. It's part of the sympathetic nervous system's fight or flight response, right? What's unusual in this case is the sudden decrease in blood pressure that causes you to lose consciousness. At the center of all this oddness is the vagus nerve, which is a major nerve that connects your brain to various regions of your body that are involved in involuntary movement, like your heart beating or your throat swallowing, that kind of stuff, right? And at the other end, your vagus nerve is connected to a region of your brain called the nucleus of the solitary tract, or the NST. Now, the NST is kind of like a toggle switch that goes back and forth between the sympathetic response, your fight or flight response, or the parasympathetic response, which is what calms you down after danger has passed. What researchers who study this kind of thing think is going on is that the NST gets some sort of confused signal maybe from the vagus nerve that causes it to decrease blood pressure as part of the parasympathetic response without deactivating the increase in your heart rate, which causes a lot of blood to suddenly be pumped away from your brain, hence making you pass out. Another explanation is that your NST simply toggles too quickly between the sympathetic and parasympathetic responses. Like it's working its joystick, like, oh, what's going on? And then you're out on the floor. Then there's another parallel hypothesis that because your NST is also in charge of mediating your disgust response, that there's some sort of mixture of fright and disgust that causes you to faint away because, again, the NST is confused. However you slice it, it seems that you can lay the fainting at the sight of blood thing at the feet of the NST. Evolutionarily speaking, passing out at the sight of your own blood doesn't make much sense, and researchers have bent over backwards to try to explain it. What they've come up with is that possibly when you faint at the sight of your own blood, say after being mauled by a bear, the bear will take you as being dead and will lose interest. Pretty lame. Another more reasonable, in my humble opinion, explanation is that this sudden decrease in blood pressure prevents us from bleeding out of some sort of wound, and that the fainting dead away is just an unfortunate byproduct of the whole thing. Either way, at any rate, whatever the case, once you're on the floor, which is usually what happens when you faint, the blood flow to your brain can be restored fairly quickly because it's a lot easier for your heart to pump blood horizontally than upwards against gravity. Do you faint at the sight of your own blood? We want to hear all about it.
So far, so good. It's really, really fairly common. Um, yeah, and people, like what he was getting at, people don't actually know why. The best idea is that, like, well, yeah, you drop your blood pressure so you don't, like, squirt so much, right? Interesting, well, okay, probably, obviously, um, it's more, so, this has nothing to do with, like, being a scaredy cat or something like that, right? It's a physiological response. It actually happens more often in males than females, which at first you'd be surprised, and then you think about it, you think, wait, in general, you're expecting women to see blood more often, fair enough, and they don't usually faint quite as badly. But yeah, it can happen to anybody. So far, so good. With that, if this lecture I don't think will make you feel faint, but if it does, like, put your head between your knees, and it's, like, kind of the normal response. Okay, so, help me out here, we're gonna spend all today talking about blood. It's really interesting. What's blood doing? It's important.
Carry.
it's carrying stuff. That's exactly what it's doing. It's carrying a lot of stuff. And the most obvious one is oxygen, right? But it's carrying lots of things. It's going to be carrying nutrients, so it'll carry things like sugar, right? It's going to carry waste, so it's going to carry, say, carbon dioxide and other wastes. It's going to carry hormones, like your blood does hormones, right? And it's also carrying heat, right? Um, if, if you feel your face flush and it gets warmer, right? It's doing that because you're feeling the blood under your skin, right? You only have more blood there than normal. If your hands go like really cold in the winter and like you really cold, it's because your blood vessels have constricted and now there's less blood there and so everything's colder. Fair enough? We're okay with this? It's also, I don't know why I like this, but it's the only fluid tissue in the human body. So it's still a tissue, but it's fluid. So the other fluid components of you aren't tissues, right? So like cerebrospinal fluid isn't a tissue. Mucus isn't a tissue. Blood is a tissue. It's got all the characteristics of it. It's connective tissue. Blood has two main types of things in it. It's got living cells, that's called the formed element, and it's got the non-living matrix, the stuff it's in, that's called plasma. So, if you go and, here, we'll look at this chart here. If you take blood and you spin it down in a centrifuge, right, so you fill up a tube with blood, you spin it down. A lot, you can separate out by density, and there's a lot going on here. The obvious ones, well, we're looking at plasma first. More than half of it is plasma, and this is less dense than the other ones. It will rise to the top. It's a lot of water, right? So tons of water there, right? Plasma, it's this fluid. Water is the solvent for all the other stuff, right? So things are dissolved in water here. This water is also why blood is so good at carrying heat, because water can hold heat really well, right? You have a whole bunch of salts. So we've got sodium, potassium, magnesium, calcium, chloride, bicarbonate, so basically baking soda. These are doing several different things. Your body needs salts to regulate a whole bunch of different processes, but a huge part of what they're doing is they're going to regulate the pH of the blood. So, like this bicarbonate especially, is going to make sure that your blood doesn't get really acidic, that your blood doesn't go really basic, that even if there are changes in the blood environment, you can compensate for that. While we're on fainting or syncope, have you seen or read or like are aware of in old movies where there's a woman wearing a corset, right? And then suddenly she gasps, something surprises her, right? And then she hits the floor. Yeah? What's happening there, amongst other things, is if she's not been breathing very much for a long time, right? Her blood has noticed this and has responded to so her blood's buffered there at like 7.4, right? It's right there where it's supposed to be. Suddenly you get a ton of oxygen in, which you weren't expecting, right? And so your blood pH changes really fast, faster than this can respond, and that's what knocks people out. Anyways, that's beside the point. So salts are going to make sure your pH is about right. It's also going to make sure that the osmotic pressure is right, because blood stays in your vessels, but it also is going to have, your vessels are also sort of leaky, right? So you don't want, you want to make sure that all the fluid in your body isn't trying to pour into your blood vessels. And you're also wanting so that your blood vessels don't just leak all their water out. So you want to have the osmotic pressure about right. That's going to do that. there are a bunch of proteins in blood as well, right? And these are proteins that aren't inside a cell, they're just floating in the blood. These are going to do the same kind of thing. They're going to help with that osmotic pressure. They're going to help with the pH buffering. They're also going to help move stuff around. So they're going to help move lipids around, right? So blood is made out of water. And so if you're going to move fats around, having proteins that can transport that is really helpful. You're going to be able to transport vitamins using some of these proteins, right? You also need antibodies in your blood for your immune response. Those are proteins. They'll be free floating. They're great. I realize there's a lot going on in this picture. Also, still in the plasma, this is where you're moving a bunch of the stuff. So you're going to have food components, right? So fatty acids, amino acids, vitamins, glucose, right? Sugar. You're going to have urea and uric acid. It's a byproduct of metabolism. You're going to have the gases, so carbon dioxide and oxygen, and then tons of hormones. We're cool with that? That's all in the plasma. Plasma's, just over a half. So this picture is showing plasma and formed elements. If you actually spin it down, you see three big bands. So you've got the plasma right here. You've got what's called a buffy coat, which sounds weird in my personal opinion. It's this like thin whitish layer, it's about 1% of the blood. It's got leukocytes, which are white blood cells, and it has platelets. So we're going to see all these leukocytes in a little while. Leukocytes and white blood cells, interchangeable terms, mean the same thing. Platelets are, we'll get platelets too, they're going to be important for clotting. And then the erythrocytes, which most people call red blood cells, again, same deal. They're about 45% of the blood. You'll hear it called the hematocrit. Anytime you hear anything heme, H-E-M, think iron, think blood. Okay, at least with like what's kind of in it generally. So far so good? Okay. Great. Before going, talk to me. If you saw blood, you'd recognize it. Fair? What does it look like? What do you expect about it? Color? Color blood? Red, resolved red. Have you seen, okay, so in your book and in like tons of anatomy books, you have some blood being drawn red and some blood being drawn blue, or at least some veins being drawn like that. Just to be super clear, blood doesn't come with a very, 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 very odd exception. Blood normally does not come in blue. You'll see if you're pale and if you look at a blood vessel, you might see like blue lines, right? You see your blood vessels there? The blood inside there isn't actually blue. Okay? We're cool with this? But blood does come in different colors based on the oxygen it has in it. So, oxygen-rich blood is bright red, like cherry red. And you do not want to see this, like, ever. Okay? Because if you see oxygen-rich blood outside your body, typically it means you hit something important, like, well, I haven't got to veins and arteries yet. You typically hit something important and big, right? And like it'll squirt. That's a problem. If you normally see your blood, like say you're peeling carrots and you take off part of your finger, right? That blood you're typically seeing is usually oxygen poor blood, and it's going to be a darker red. Blood pH is smack dab at 7.4 pH, right? So basically neutral. It needs to stay in a fairly tight range. It spends half its time trying to be buffered. Like, blood really cares about being buffered. Um, Blood's slightly warmer than the rest of your body, right? So you're expecting it to be about 2 degrees warmer than body temperature. You have about 6 quarts of blood, depending on how big you are, which is, impressive. Um, yeah. You can imagine like a liter soda bottle. You got about 5 or 6 of those of blood inside you. Unless you're a pregnant person, in which case you have so much blood, it's bizarre. Um, if you actually want to find out how much you have, you can just take about 8% of your body weight. We're good? Great. Alright, I'm not too excited about this one. Plasma's water with all these dissolved substances. So many dissolved substances. Nutrient salts, gases, hormones, plasma proteins, waste products. The plasma proteins are very important, right? Have you ever, so you're doing something, I don't know, but you get a cut and it won't clot up? Has this ever happened to anybody? Okay. Oh, lame story of my own. Once upon a time, I was washing dishes and the cup shattered around my hand, which was surprising to me. And so I slap a Band-Aid on my finger, right? 24 hours later, it's still not stopped bleeding. So I wandered to the health center and they had to explain the lamest injury I've ever had. They're like, "Why are you here at the health center?" I'm like, my finger is bleeding. They're like, "All right, you're gonna have to wait." I'm like, yeah, okay, fair enough, because they've got people who actually have real problems. Good news though, because I thought they always thought it was gonna be dumb. And the friendly nurse was like, "Okay, here, have you tried putting a Band-Aid on?" I'm like, "I've tried that for hours." She puts it on. She's like, "Huh, it won't stop bleeding, will it?" "Yeah, no, it won't." They're like, "Okay, we are gonna put pig clotting protein on you." Okay then. So they dump some of that stuff on and it clots right up. I'm like, "Oh, well, I guess that's good." Anyways, all that to say, your blood is super, super fluid, right? It's liquid, it's gooey, right? We're sold on that? And you need it to stay fluid to move appropriately. Fair enough? You gotta have it be moving. But if the integrity of a blood vessel is broken, you need to be able to fix it, right? You need it to be able to not all completely leak out. Because if you have if you something like a garbage bag full of water, right? So long as that membrane, that edge stays intact, you're keeping the water inside the garbage bag, right? But as soon as you pop a hole in that, right? Like you put a hole in the very bottom, doesn't matter if the hole is big or small, so long as there's a hole, you'll have the water come out. It might take longer for a tiny hole, but it's coming out, right? So, same deal with the blood vessels. If you get a hole in it, you need to be able to fix this. It needs to be self-fixing. You can imagine um, those self-sealing tires. Have you ever seen those, right? You get a hole, but it fixes itself. Um, Clotting proteins are going to get this done, right? So, um, yeah, lots of things going on. These proteins, tons of them in plasma. The liver is making these, so that's important. Blood's weird because some of its stuff, like the formed elements, the blood cells, you're expecting the bone marrow to be making, and then other stuff you're getting from, say, the lungs, right? You're getting gases in. Other stuff you're getting, like nutrients you're getting from the digestive system. The liver is handing off all these proteins. Things are coming together from lots of different places. Anyways, okay, so you've got the clotting proteins. You have antibodies, which are going to be really important. And you also have albumin, which is regulating osmotic pressure. Fair enough? Okay? Questions? The blood plasma is where you're going to try to regulate blood pH. If your blood gets too acidic, it's called acidosis. And if it becomes too basic, it's called alkalosis. The respiratory system and the kidneys are going to help try to bring that back to balance. Depending on how much time we have, we might go into this in depth, but I'm not sure how we are in time. We're okay with the plasma portion of blood? The goo portion? Okay. The other portion are these formed elements. So the stuff in the plasma, those things have never been a cell, right? So you have these proteins floating free. You've got these antibodies floating free. You've got these salts and these sugars and these hormones, right? But no physical cells. The formed elements do come from cells. So if you look at a picture like this is blood. You see these little, the ones you see a lot of? You should see three different kinds of things going on. You should see a lot of these little tiny, they look brown here on the slide. A few of these big purple ones, and lots of these little tiny chunks of purple things, right? The red blood cells, erythrocytes, there's a lot of them. A lot of these cells, right? There are fewer white blood cells, they're the ones I'm saying purple. And then there are platelets, and platelets are, it used to be a cell, but then it got fragmented, and the cell chunks are what you see as platelets. Alright, so that, yes, may have protein and stuff, but it used to be part of a cell, and it got torn to shreds. So far, so good? These things all have different jobs. What's the job, you don't have to know off the top of your head, but you might. I bet you probably do, actually. What's the job of these red blood cells? The standard, boring, run-of-the-mill red blood cell. What is it supposed to do, basically? You know, I know you know. Carry oxygen, are we okay with this? Yeah, okay, right? They're carrying oxygen, and they're really, really good at it. You can see a little bit on this picture. Your slides have more notes, but you can see a little bit on this picture. You know the shape of Surt's mints, right? Where it's a ring and it's like in on one side, in on the other side, right? It's called biconcave disc. That's the shape of these things. Red blood cells are basically the opposite of muscle cells, of skeletal muscle cells. So skeletal muscle cell, super long, has lots of different nuclei in it, right? Red blood cells are bizarre because they do not have a nucleus at all. And that should be weird to you, right? Because like normal cells have nucleus. So what's happening is red blood cells are getting formed. You're forming up this red blood cell, and the cell starts with nucleus, but you get rid of everything that you don't need. The idea is red blood cells aren't going to last forever. You don't need them to last forever. We need to basically just get a bag full of hemoglobin. We need to get this bag, stuff it full of hemoglobin, and have it just float around the body. So yeah. Doesn't have nucleus, doesn't really have many organelles, period. It's legitimately basically a bag full of hemoglobin. And you have a lot of these little guys. You have about, nobody's actually counted, but you can make some good guesses. If you get a cubic millimeter of blood, which is not very much, you're expecting about 5 million red blood cells. Right? Like, a lot. A lot of these. So far, so good. Red blood cells, bags of hemoglobin. Hemoglobin is awesome. It is so good. Um, it's this protein. It has iron in it, which is sort of odd for a protein. So it's got this protein, and it has these metal portions in it. It's got 4 spots that hold oxygen. Okay? And when I say oxygen, I'm talking about molecular oxygen O2, just for the record. Hemoglobin is super interesting because it can hold really, really tightly to oxygen, which is a good thing, right? But help me out with a thought experiment here. Hemoglobin grabs onto oxygen and holds it, right? Which is excellent when you're someplace that has a lot of oxygen. So you get hemoglobin right next to the lungs, there's oxygen there, it grabs it, holds it on for forever, right? Cool with this? Now, if this hemoglobin moves through the blood and ends up down in my toe, right? It's holding on to oxygen. I don't want the hemoglobin to have the oxygen. I want the oxygen to leave, right? So, do I want hemoglobin to still hold the oxygen, or do I want it to get rid of it? Yeah, you want to get rid of it, right? But that makes a really weird type of molecule that you want. Sorry, the type of protein that you want. You want this protein that holds oxygen really, really well, because if it doesn't hold oxygen, right, you can't carry it. You want to hold it really strongly, but you also want it to let go of it easily. Fair enough? Do we see that? The trick that it uses, and again, this is, if we have more time, we'll go into depth. The more oxygen hemoglobin has, the better it can hold oxygen, right? So, if 3 of these spots are all holding oxygen, it's the shape of the protein changes slightly, and it's really easy to hold a 4th oxygen, right? So, if there's a lot of oxygen, it's really, really easy for hemoglobin to hold oxygen. If there's only like if there's only a little bit of oxygen, it's the shape is such that it's harder to hold any oxygen. So that means if you're in a place that has a ton of oxygen, and you get if you have a ton of oxygen, some oxygen will end up here, right? And having oxygen there makes it easier for other oxygen to be carried, right? But then when you get to a low oxygen environment, say your foot, because of diffusion gradients, some oxygen is going to leave, right? It's more likely that a little bit of oxygen comes off. And once a little bit of oxygen comes off, the hemoglobin molecule is less able to hold any oxygen, so some comes off. It's easier to get rid of more, which makes it even easier to get rid of more, easier to get rid of more. Do you see that? So if there's a lot of oxygen, it holds oxygen really well. If it's in a low oxygen environment, it dumps oxygen. 1 hemoglobin molecule, 4 oxygen binding sites. Each red blood cell has about 250 million of these molecules. These molecules. Right? So you have like 5 million red blood cells per milliliter of blood, right? And each of those little red blood cells is a bag stuffed with this stuff. We're good? We're okay with this? Great. You've heard about problems with blood, probably, maybe? You've heard of like sickle cell disease? Heard of this? Okay. There are lots of problems you can get with red blood cells being out of whack. The kind of catch-all term, there are other problems that can happen with blood, but the catch-all term is anemia if the cells can't carry oxygen normally. So, sickle cell anemia is when you have oddly shaped hemoglobin, and it ends up where you end up with sickle cell red blood cells. It's known exactly where the mutation is. This is a normal red blood cell, right? this biconcave disc kind of goes in on this side. The other side looks the same. Carries oxygen beautifully. Um, if it's switched out, it doesn't carry oxygen quite so well. Um, and that's a problem. It actually, just for the record, I don't know why this is interesting. It's interesting to me. If you're homozygous for the sickle cell trait, right? If you got if you got this from both parents, that's really scary. Like it's makes life much more challenging. However, if you're heterozygous for it, your blood's pretty much normal, except you're way better at surviving malaria. Just so you know, which is why that's the thought of why the trait's still around, because it's somewhat protected against malaria. Okay. Thought experiment number 2, or I don't know, I can't remember what number 1. Red blood cells are, and you might actually know this, there are several sports here. Red blood cells are great at carrying oxygen. Fair? Okay. When you do sports, or any athletic thing that involves a lot of work, right? You want to carry a ton of oxygen to your muscles. Fair enough? Um, have you ever heard of people basically donating blood to themselves? So they'll get blood out of themselves. You've heard about it. Jake, can you tell us about it?
And just sort of like athletes cheating the folks that stick in blood in the fridge for like a month, I guess.
Yeah. So right. So the ethics of this aside, it makes sense with what they're trying to do at first, right? So you're like, okay, so if I take blood out of me, right, the body's gonna make more blood. You're like, oh, you lost them. It's gonna make more, right? Cool. And the body has a certain amount that it's expecting, and there's a certain proportion of red blood cells that it wants, right? But then if you have your blood, that's legitimately your blood. So like if somebody does a DNA test on you or something, they're not gonna find any foreign elements in it, right? You take your blood out, you spin it down and just get the red blood cells, and then pump them back in, right? Your body doesn't recognize it as foreign, right? It's you. You now have more red blood cells per cubic millimeter, right? So oxygen carrying ability is better. Like it is, legitimately it is better. Aside from the ethics, can anybody think of a problem with this? Yeah. Yeah. Absolutely. It can be a real problem. There's actually a version that's natural in polycythemia. It's when you can either have abnormal red blood cells or too many of them. Um, it can happen because you've got bone marrow cancer. It can happen um, certain times of altitude. It can happen, but or you can give it to yourself by just stuffing more red blood cells into you. But what you do is normally you normally have this plasma red blood cells, right? Mixed together, it flows. If suddenly you have a lot more red blood cells, your blood is thicker. It's goopier. And yeah, it carries oxygen better, but you now have new problems because it's hard to move it through the vessels. So you'll hear about athletes when they do this. Don't do this. Oh my gosh, don't do this. There's no sporting event worth it. I'm just saying. um, they'll have to set their alarms for every couple hours so they can get up and exercise so they can keep blood moving because otherwise, they might die. See this? Um, it makes blood thicker and goopier. Don't do this. The treatment, if you actually have this disease as disease, the treatment for it is you just like give blood often. Like legitimately, they're like, oh, well, let's pull some off. Um, yeah. Oh, the blood doping, like if you do it yourself, View it yourself. Yeah, blood cells. Red blood cells have a life expectancy. So yeah, you if you were doing this, you'd have to keep doing this. But if you did it once, um, in a month, you'd be back to normal. Yeah, you'd have to keep doing it. Yeah, yeah.
Is this kind of similar to like what horses do?
What?
Horses, they store, I guess it's not similar because it's not excess, but they store like a third of their red blood cells in their pancreas at any given
Oh,
moment. And then when their fight or flight instinct kicks in, their pancreas contracts and it
that makes sense.
dumps all the red blood cells that it's stored so that
Yeah,
it has more
it can help.
oxygen and stuff.
That's also awesome. Like
I guess it's
your
not,
spleen will do that too a
maybe
little bit.
it's the spleen that contracts, not the pancreas.
Yeah, no, humans have the same deal. It'll do it, and
Yeah.
it's not a problem. Like it's just kind of like this backup. The spleen is bizarre. Nobody, well, okay, science knows what the spleen does. It's an organ that's super underappreciated, in my personal opinion, because you don't actually need it, but it's a helpful backup. It's there. It does other things too, but mostly it's sitting there holding a bag of blood, being like, "Let me know if you need me."
Yeah.
Yeah, it's it's cool. We'll talk about the spleen next semester um, with the immune system because it doesn't really go anywhere exactly. But yeah, no, I didn't know horses did that, but that makes sense.
Yeah.
Horses also have so much blood,
Yeah.
like a
It's like,
lot.
it's like a gallon of blood per 100 pounds.
Yeah,
So normal horses are like 10 to 12 gallons of blood.
that's a lot of blood. Sorry, I like horses. They're also bigger than 5-year-old me thought they were. Does that make sense? They're like, oh, horsies. And I'm like, holy cow, they're big and have weird teeth, but that's okay. Um, yeah. So yeah, you totally have a backup of blood. That's great. And at any given time, Bray makes a good point. At any given time, all of your blood isn't in your blood vessels. Um, and all of your blood vessels aren't full either. So you've got a ton of blood in your kidneys. You've got a fair wad of blood in your spleen. You've got blood, in your skin, and depending on the situation, you can change where blood is, right? Okay, so red blood cells carrying oxygen, super important. Interestingly, well, sort of interestingly, if you're worried about carrying oxygen in red blood cells, you're not worried about having a special carbon dioxide carrying molecule. You're going to dissolve that into plasma, amongst other things, and just go from there. So, red blood cells, you also have white blood cells. You need these. I mean, you need all these parts. White blood cells are going to keep you from being dead. They're going to be your defense against diseases. Um, they're complete cells. So, red blood cells were a cell, but you I mean, they're still cells. But they were a normal cell, but then you took out a bunch of the organelles, you took out the nucleus to give them more room for hemoglobin, right? White blood cells, they have a nucleus, they have organelles. They can move in and out of blood vessels. It's called diapedesis. And these little guys move by amoeboid motion. So they roll along the inside of the vessel. And if they feel like it, in response to chemical signals, they'll squeeze through the blood vessels have overlapping cells, and they'll squeeze through in between it and go out into the body. Um, you have a lot of them, but not nearly as many as you have red blood cells. You have some white blood cells, you have tons of red blood cells. And white blood cells are responding to chemical signals. So there are a bunch of chemical signals that your body sends, and white blood cells respond to those, typically go towards higher concentrations of these signals. We're cool? Anything white blood cell, you'll hear with Luke, this idea here. So you've heard of leukemia? Yeah? That's a problem with the leukocytes, with the white blood cells. If you've got funky numbers of white blood cells, you could have lots of different problems. Um, if you have lots of leukocytes, you suddenly have a lot per unit, right? So blood you typically measure for, if you're measuring like cells in it, you're measuring by cubic millimeter. Um, if you have a ton of them, you assume that you have an infection, right? Because the body's trying to fight an infection, have white blood cells go great guns, try to take out the infection. Leukopenia is the opposite idea, where you don't have very many of these things. Some drugs will get this done. A lot of anti-cancer drugs get this done, which is why if someone's on cancer treatment, often they need to be really careful about like not getting a cold or something, right? Because they just don't have as much to fight an infection with as they would if they weren't taking the anti-cancer drugs. We see that? And then leukemia, it's this odd combination of the bone marrow has gone cancerous, so it's just going to crank out white blood cells. And there are other problems too, but that's a large portion of it. We're okay? The next portion is just straight up things to memorize a little bit. Leukocytes, white blood cells. So like red blood cells come in one variety, like red blood cell. Like you see it, you're like, this is a red blood cell. White blood cells have lots of options for them. There are lots of different types of white blood cells. And we're gonna look at them. So granulocytes, they look grainy and they're lumpy. So there are three different types there. And then you have agranulocytes, which they don't look grainy when you stain them, and their nuclei are smooth, they're not lumped, and we'll look at these here. Just for the record, if you're trying to remember which one's which, the helpful mnemonic is never let monkeys eat bananas, neutrophils, lymphocytes, monocytes, encephalals, and basophils. Also, while we're on this is not super relevant. It's not relevant at all, but I feel like it's a public service announcement you need. You know when you eat bananas? Yeah. Okay, you eat bananas, and you have the like curvy part of the banana and then the little stick part on the end. And most people break the little stick part and then do it this way. You can do that, that's fine, but that's so backwards. First of all, you're eating the banana upside down because bananas grow banana fingers up. So A, you're eating upside down. B, monkeys eat it the other way. And C, if you eat it the other way, you have a nice little handle to hold the banana. Just so you know. Thank you for listening to my public service announcement. I think people eat bananas upside down. And I also think if you eat bananas a normal way, everybody who sees you doing it thinks you're weird, and it's just not fair. Sorry, moving on. We're looking at the granulocytes here. So we're looking at white blood cells. Do you see how it looks grainy? It's so it looks grainy because the projector looks grainy. You see the graininess there? You see the graininess, and you also see that the nuclei, which is stained purple, dark purple, looks lumpy, bumpy. These ones are neutrophils. There are a bunch of them. These ones are, you know when you get an injury and you end up with pus? What you're seeing is tons and tons of dead neutrophils. So neutrophils come in, they're trying to help, they sacrifice themselves for the cause, they surround pathogens, they gulp the pathogen, right? And neutrophils die. And so pus is just a ton of dead neutrophils that you're seeing, right? And yeah, they'll stain grainy, you'll have a bunch of them. Another type of granulocytes are these little guys. They're not quite so common. What they do, amongst other things, they play a role in allergies, but my personal favorite thing they do is they take out parasitic worms, and you need to watch this. And I don't know, maybe before today you didn't think about how, because, so like, your blood is a great spot for parasitic worms, right? It's warm, it's wet, there's tons of nutrients, plenty of oxygen, right? Few things to eat it, right? Like, if you're a parasitic worm, the vascular system looks like a great spot. But, speaking personally, I really do not want parasitic worms living in my blood. Like, that creeps me out on a deep emotional level. Also, it's not good for me. But okay. This says just white blood cells. See your parasitic worm, buddy? Okay. Watch it. Yay! I know, right? It's very nice to have these. They also are involved in allergies. Okay. You also have basophils. The,
Immune system under the microscope.
no.
You're seeing on your screen here.
Fine. Basophils, there aren't very many, but they're really big. Nice, chubby granulocytes. They've got histamine, or they'll release histamine. So like, you know when you've got allergies or something, you'll take an antihistamine to stop it. These guys are releasing histamine. They're triggering an inflammatory response in your body. They're like, hey, something bad is happening. Trigger an anti-inflammatory thing. They'll also they have something called heparin in them. People heard of heparin? Okay. It's a really powerful anticoagulant, meaning your blood clots up a bunch of places, right? But you also want to make sure blood keeps flowing in certain places, right? So it doesn't gum up. Heparin is going to get that done. It's going to keep things moving. And you only have a few of them, but they're important. Okay. But you see this picture? Do you see how it still looks grainy? Right? The next set that we're looking at are the ones without graininess, granulocytes. They'll stain just like one color. They won't look lumpy, right? So you see the difference here? Granulocytes, agranulocytes. The lymphocytes, these ones are the ones that are like the classic immune cells. So neutrophils are important for the immune response, right? But they're not particularly specific. Neutrophils just see whatever they see and they just like gulp it, right? Lymphocytes are going to be working for making, well, they come in B lymphocytes, they come in T lymphocytes. They're going to need the blood that like learns stuff about the immune system. They're going to learn about what your body has seen before or what to fight. And you have a fair number of them. So far, so good. With vaccines, your body's trying to. Vaccines are trying to do many things, but the basic idea is you're trying to teach these little lymphocytes what to look for. You also have monocytes. I don't like this picture because I feel like it looks grainy still, but it's not, apparently. Monocytes are the biggest white blood cells you have. They're like, okay, it's hard to tell based on the picture, but do you see the red blood cells for scale? Right? Monocytes are bigger. They act as macrophages, so they're basically a fight infection, and they're going to go around destroying invaders. So far, we're good? So we've had red blood cells, we've had white blood cells as formed elements. The last formed element we're looking at are these little guys called platelets, right? So platelets are chunks of cells, and the chunk of cell that they come from is something called megakaryocytes. It's this huge cell, it's got lots of nuclei in it. It ruptures, and then you have lots of little chunks of this stuff. And you need it to clot the blood up. And you have a lot of them in you. Okay, we are still not going to finish all of this today, and that's fine. Oh my goodness. Fine. While we think about it, have you all heard? I don't know how much you're. I'm aware you're following a lot about COVID. How much about COVID are you people following? Like a lot? Yeah. It's so weird. Amongst other things, it looks really blood-based, right? It looks like it's, I don't know if you've heard, like, certain blood types work better for this if you're, or worse. Have you heard about this yet? Yeah. The coronavirus is weird because it does look like it's impacting blood oddly. It's also, for people who've gotten really, really sick from it, it looks like it's forming tons of little clots, like tons of little clots in their lungs or tons of little clots in their brains, which is weird for a coronavirus to do. This virus is so weird. And for people, the long haulers, it looks like it's basically activating these histamine kind of cells in blood and just encouraging them to like keep going forever even after you've cleared the virus. It's weird. Sorry. This was me trying to tie it into current events. Okay. Back to non-current events, just things that are happening. When you make blood, well, you want to make blood. So, not counting where you get water from or where you're getting some of the plasma proteins or the salts, getting the formed elements from blood, that's happening in the bone marrow. Alright? So, all blood cells are going to come from the common ancestor blood cell. And they're going to be called hemo, right, so for blood, cyto, right, for cell, and blast, right, for formation. So there are these blood-forming cells. You start from there, but you go two different ways. You can go the lymphoid route, which is going to make white blood cells, lymphocytes, and then the myeloid stem cells are going to do the rest of them. So here's our picture of where we're going for. Ancestor of all the cells, they'll go to either lymphoid stem cells and then to lymphocytes, the whole, lymphocytes, or you'll go to myeloid stem cells, which do like all the other things, right? So red blood cells and platelets and the rest of the white blood cell types. Cool. Casey, this is going to answer your question on how long after you add extra blood to your body does it take to go? Because you're making red blood cells. Your body's making red blood cells all the time, right? But red blood cells don't have nuclei. So if you don't have a nuclei and you don't have, say, nuclear DNA, can our little eukaryotic cell, can it divide? It doesn't have this DNA to do it? No, right? Red blood cell, once it's made, right, so its ancestor cell, right, this stem cell, it could divide, it could grow, etc. But once you're here to a red blood cell, you're not growing, you're not dividing, you're done. So they can't grow, they can't divide, they can't even make their own proteins. They get what they get, they get what they start with, and then that's what they have. So they last just over a month. Sorry, just over 3 months. Sorry, I don't want to think that. They last just over 3 months. They wear out pretty quickly. And the spleen, again, underappreciated organ, or the liver, because blood flows through everything, right? Blood flows through the spleen of the liver. When it sees a questionable red blood cell, it's going to be like, and just destroy it. We're good? And this is happening all the time. You're destroying these. You're destroying old ones, making new ones. And you're replacing them, again, through cellular division in the red bone marrow. Yeah? How this is controlled? This is controlled by a hormone. So red blood cell production is under the control of this hormone, erythropoietin. It's going to respond to oxygen levels. So the kidneys watch for oxygen in the blood, and if oxygen in the blood drops, the kidneys dump the hormone out, saying, bone marrow, make more red blood cells. So here's our beautiful picture, right? You have low blood oxygen. This could be for a whole bunch of reasons. You have low blood oxygen because you don't have enough red blood cells, or maybe you have plenty of red blood cells but the hemoglobin doesn't work, or maybe you're someplace that has like a really high altitude and you don't have very much oxygen. Regardless, the kidneys notice, oh, I'm not seeing as much oxygen as normal. Oh yeah, technically the liver can do this a little bit. It's basically the kidneys. Notice this, panic, send a signal to the red bone marrow saying, get on it. And the red bone marrow cranks up red blood cell production, which, if all goes well, right, if these are able to carry oxygen appropriately, you have more red blood cells, you're carrying more oxygen, the kidneys notice this and stop sending the signal to make more red blood cells. We see this? We're okay with this? If you were in, well, this is why, and this is totally legitimate. Have you ever heard of athletes training at altitude before they compete? Yeah. And that's fair, that's fine. This is what they're doing, right? So they've got red blood cells in their body just here, now, everything's fine. The kidneys are cool with the amount of red blood cells they have. I mean, they're just keeping it normal, right? But if you go to a low oxygen environment, suddenly the kidneys are going to notice, like, hey, I don't have as much oxygen as I did before. It's going to crank up the production of red blood cells, and you'll get more. You'll get better oxygen carrying ability. So then as you come back down from altitude, you'll still have those, right? Again, though, it doesn't last forever. It's going to go away after a little while. We're good? This is actually why there's some marathons that are way harder to run. So like, I can't remember which ones they are, but there's some marathons that are run at fairly high altitude. And so people who live in that general area, they're training for them there, they're fine. People who've been training for them at like sea level and then come, they're like, it's very hard. This also, you can mess this up other ways. So like, if for whatever reason the protein hemoglobin isn't working right, it's not folded correctly, there's something wrong. Ooh, okay. Let's say the hemoglobin's not working. It's just the protein doesn't fold quite right. It doesn't carry oxygen very well. Do you expect that you see somebody with the person who has this problem with hemoglobin, do you expect that they have a lot of red blood cells or very few red blood cells?
Hemoglobin?
Yeah, so let's say everything works fine except hemoglobin doesn't carry oxygen very well. It's not good at its job. Maybe it's just not super effective.
It would be a lot, wouldn't it?
Yeah! How come? You're so right. Explain.
They need more red blood cells to carry less oxygen.
Yeah.
Make up for less oxygen.
Yeah, absolutely. So just because you see a lot of red blood cells in a cubic millimeter doesn't mean like, oh, this is fantastic, everything's going well. It's like, oh, maybe things are going very poorly, and this is the compensation mechanism. We're okay with that? Okay, if you're going to make white blood cells or platelets, you have a bunch of hormones that are involved in it, and we're just going to leave it there. So, red blood cells, your kidneys are driving this. White blood cells, lots of things. And platelets also lots of things. The last concept for today, we have time for this. Man, I thought I'd be at a minute per slide, but apparently not. Oh my goodness sakes. You want to be able to stop blood from leaking, right? So you need hemostasis. Hemostasis is not the same thing as homeostasis, okay? That stasis idea is the same, but this is now blood being balanced, okay? Three main phases that happen here. You have what's called a vascular spasm, platelet plug formation, and then coagulation, which is just the fancy term for clotting. This is what it looks like, folks. Something has happened and you've broken your blood vessel, right? It happens lots of different ways, but that blood vessel gets broken, chemical signals are released, and a vascular spasm happens where that blood vessel spasms, it constricts. It doesn't shut off completely normally, it doesn't completely crank itself closed, but it does shrink in size. What does that do for how much blood you're losing? Are we okay with that? It's going to make it so that there's less blood coming out, right? Because you just narrowed the hole. Fair enough. So around blood vessels, you have smooth muscle. The smooth muscle is going to clamp down and it's going to make it so you're not pouring as much blood through this. Okay? And then this happens. You have all these little platelets, which are chunks of what used to be a cell floating free in your blood, right? When there's a break in the blood vessel is normally there. When it breaks, you have collagen fibers that are now exposed. They used to be like all tied up, but now you broke and they're exposed. And platelets stick. They stick to these collagen fibers. And once one sticks, other ones stick more. So once an anchored platelet's there, it's going to dump a bunch of chemicals out that's going to get more platelets to glom on. And so this is one of the few positive feedback loops your body actually has. So as you get the signal that some are sticking, it's easier to stick more, right? They pile up and they form what's called a platelet plug, and it's going to glom across this. So you had your break. You have sticky sides on both sides, right? And then it gets really, really sticky for platelets, and they stick and they clog that area up. Then, and this is all trying to happen about the same time. No, 5 minutes. Yeah, we're good. We've got this. Injured tissue, like when you break the cell, injured tissue throws chemicals out, right? And your blood's gonna respond to that. So lots of things are gonna happen, but you're going to here's a picture. This is yeah. Okay. What's gonna happen is this. You've had a break. You got a bunch of signals saying you need to coagulate. Some of those are going to be intrinsic, so platelets that are like on and being activated, this collagen that's been exposed, right? They're going to prompt this coagulation. Also, tissue factor, which you got because some tissue was broken, that released what's called tissue factor, and that's going to encourage this. You have a whole bunch of chemicals that are going to play a role. You got something called prothrombin activator. You're going to turn on a series of molecules. The upshot is you have these little tiny chunks in your blood that aren't actual fibers yet. But once you send the signal, they're going to fiberize. It's not really the word, but they're going to become fibers. They're going to turn what's called fibrin. And then you have this mesh around the whole system. So those activated platelets that you had, the cells that were damaged sending a signal to get the mesh in the blood to form, that's going to form, this mesh around this clot, and you'll catch red blood cells, because you had this mesh, you'll catch red blood cells, you'll catch platelets, and you'll clot. And it looks like that. You see it? So we've got this fibrin mesh that acts kind of like a net, and then chunks and red blood cells get trapped, right? And you're going to clot there. This is going to happen about 3 to 6 minutes, right? Which you probably know, right? You cut yourself, you start to bleed. It's going to take about 3 minutes for it to close up, right? The bigger, the deeper, the harder it's going to be, but about 3 minutes should get you there. And then the clot eventually gets broken down. Yeah? Oh, that's all we have time for. On Thursday, we'll talk about what happens if you, say, get a clot in, like, a blood vessel of your heart. That's bad. Don't do that. Remember to take your exam. I'll send an email, too, saying remember to take your exam.